Welcome back to another lecture series on fluid mechanics. It's me, your tutor, Ganasam Singh Rembam. In this series, we will discuss or consider on the topic compressibility and bulk modulus, surface tension and capillarity. So if you have not subscribed to my channel, please hit the subscribe button for any new updates on the upcoming lecture series. So let's see the first topic, compressibility and bulk modulus. Compressibility, how compressible a fluid is. So what does it mean? It says how much the volume or density of a given mass of fluid can be changed when there is a change in pressure. Okay. Then how do we define or characterize the compressibility of fluid? We can do it by a property called your bulk modulus. And then what is the relationship between this compressibility and bulk modulus? We have the relationship between them as compressibility is the reciprocal of the bulk modulus and given by capital K. Then how do we define or mathematically express this bulk modulus? We can do it as capital K is equal to dP divided by minus dV by V. So I am using this as V, okay? So which is nothing but the ratio of increase in pressure or compressive stress to volumetric strength. Or in other words, we can say is as ratio of differential change in pressure needed to create a differential change in volume dV of the original volume V. You can define it like this also. Okay. So let's try to understand with a diagram here. See, I have shown given a piston cylinder arrangement here. So in this, let this V, inverted V, be the volume of gas inside this cylinder, and let this P be the pressure, initial pressure when the volume of gas is V. Say, suppose after some time we have increased the pressure to P plus dP. Then what will happen to the volume of gas? Definitely it will get decreased to dV. Then your volumetric strength becomes minus dV by V. Then what does this negative sign indicate? It indicates a decrease in volume inside the cylinder when your pressure is increased. Okay, then finally we can come back again to the equation capital K is equal to dP divided by minus dV by V, which is equal to, after some rearrangement, minus dP into V by dV. Then finally we have compressibility is equal to 1 by K, which is the reciprocal. So compressibility is the reciprocal of the bulk modulus. Okay, let us also see the relationship that exists between the bulk modulus as represented by K and pressure P. Okay, first let's see for the isothermal process. So we know what is isothermal process, a process in which your temperature remains constant. Okay. We have the relationship between K and pressure P for a gas as P by rho is equal to constant. How it is coming? You can see I have given here on the right hand side. You know that PV is equal to RT. So V is the specific volume, so P by rho is equal to RT. Okay. So P by rho is equal to constant here. Now we differentiate the above term. So differentiating we get P by V is equal to constant. P into dV plus V into dP is equal to 0, or P dV is equal to minus V into dP, or P is equal to minus V into dP by dV, which is given as equation 1. Now we let's substitute the value of P from equation 1 in the equation of bulk modulus from the previous one. Okay, so we have the equation of bulk modulus as K is equal to minus dP by dV into V. So this is also equal to from equation 1 we have as the value of P. So finally we have K is equal to P as the final relationship. Next, let's see the relationship for the adiabatic process. We know that the in adiabatic process your heat transfer is 0, and we have the relationship given as P by rho to the power K is equal to constant, or P into V to the power K is equal to constant, where your K is given as ratio of specific heat of a gas at constant pressure and constant volume, and we have the value of K for ER as 1.4. So we have the equation as P into V to the power K is equal to constant. So let's differentiate this by taking first function and second function. Then we have differentiating P into d V to the power K plus V to the power K dP is equal to 0, P into K into V to the power K minus 1 dV plus V to the power K dP is equal to 0. After simplifying, we get the equation number 2 as Pk is equal to minus V into dP by dV. Now substituting the value of Pk from equation 2 in the equation of bulk modulus, so we have the equation of bulk modulus K is equal to minus dP into V by dV. So finally we have K is equal to P into K, where this capital K is the bulk modulus, is equal to pressure into K. This K is the ratio of specific heat of gas at constant pressure and constant volume. Okay, I'm pretty much sure that you have seen such type of insects floating or running in small water bodies or ponds in your locality. We call such insects as water strider. Okay. Also, you can see another image of water droplet, which is seen bouncing off from a water surface. So why I'm showing you such pictures? The next topic which we will discuss is causing or like related to such phenomenon happening. Let's discuss the next topic, which is called surface tension. We will see the definition part first. So how can we define surface tension? We can define it as a tensile force acting on the surface of liquid in contact with a gas. Or in another way, we can define it as the force per unit arc length which exists on the interface between two immiscible fluids, which are air and water. Okay, so basically surface tension is the kind of force which develops on the surface of liquid and which causes the surface to behave like a stretch membrane and over the fluid mass. Okay, and we denote the surface tension by the Greek letter sigma, and we have the unit in SI as Newton per meter. Then what is the force which is responsible for the surface tension? This surface tension is caused by the unbalanced cohesive forces at the fluid surface. Okay, so let's try to understand this with the help of diagram. You see here on the diagram we have some volume of water inside an open container. Okay, clear? Now you can see this dotted line here, dot 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 here. This is the air water interface, and we have diagrammatically shown two molecules A and B. This molecule A is situated at the interior part of the vessel. Okay, so what happened here at this part is, here the molecules A are attracted equally to each other in all directions by the nearby water molecules. Okay, that means the resultant force is 0 here. Okay, we are talking about the cohesive force here. Okay, but when we go to the molecules B, it will experience a resultant downward force. Why it will experience a resultant downward force? Because we do not have any force, upward force. So the forces only is acting downward. So that is why all the molecules on the surface of the liquid will have a downward force. So because of this, the free surface, it behaves like a stretch membrane under the tension of the surface of the liquid. Okay, this is the phenomenon behind your surface tension. We will also see some of the expression for pressure intensity for some cases. Okay, surface tension, first case is for liquid droplet. We can have the expression for pressure as P is equal to 4 sigma by D. Second one, hollow bubble, we have the expression as P is equal to H sigma by D. And last one, liquid jet, we have the expression for P as sigma into 2L by L into D, where your sigma is the surface tension, P is the pressure intensity, D dia of droplet, and L is the length of jet. The next phenomenon we have is capillarity. So how can we define capillarity? It is the phenomenon of rise or fall of a liquid surface in a small tube relative to the adjacent level of liquid when the tube is held vertically in the liquid. So this is the definition of your capillarity, and we can have two cases here. First may be your capillarity rise, and another may be your capillarity depression. Okay, and generally we express the capillarity in centimeter or mm of fluid. Let us try to understand with the help of a diagram. I've given two diagrams here on the right side. So you see we have a vessel here. We have a vessel here containing some amount of water. Okay, and in that when we insert a small diameter tube, preferably a glass tube, into the water, the level of water rises to a height h, which is with respect to the relative height of the adjacent level of the water. Okay, so in such case we will say that we are having a case of capillary rise, because the water is rising up to a certain height h in the small diatube. Why is it happening? It is happening because we have a wetting liquid here. And what does this wetting liquid mean? In a wetting liquid, the adhesive force overcomes the cohesive force. So here what is happening is that the adhesive force between the wall, that is the wall of the tube, and the water, that is strong enough to overcome the cohesive force between the water molecule. Okay, so in such a case we have a capillary rise. Now see the next one. This is the case of capillary depression caused by a non-wetting liquid. So non-wetting liquid means the cohesive force is more than the adhesive force. Okay, so here the adhesive force is weak as compared to the cohesive force, so the liquid will not wet the surface, and the level of the liquid in the tube will actually be depressed. Okay, will actually be depressed with respect to the relative level of the water in the level. So this is the phenomenon of capillarity, and we have two cases here: capillary rise and capillary depression. Let us also try to see the expression for capillary rise or capillary depression. Okay, see in the diagram I have drawn a small vessel containing some amount of water. Okay, we have a case of capillary rise here. Let your sigma be the surface tension, theta be the angle of contact between liquid and gas tube, and the upper surface of the capillary rise, we call it as meniscus, and we have a concave surface here, and your the height of the liquid is represented by small h. Okay, so see here this theta, practically how do we measure it? So we can do it by, see, you try to find out the middle of the meniscus. Say R is the middle, R point. Okay, then from the point R you draw a normal to the point where the tip of the meniscus and the wall of the glass interacts. Okay, so when you find out this point, then from here again you draw a tangent. Okay, from this point you draw a tangent, so the theta is the angle between this tangent and the wall of the glass tube. Okay, so that's how you can find out your theta. Now let's go to the derivation again. What we'll do is we'll try to find out the forces acting. Okay, forces acting in the edge. So generally what we'll do when we see what are the forces acting, we see one is weight of the liquid and the vertical component of the surface tensile force. So let's try to see the vertical forces. So first one, weight of the liquid of H. So how will given? Weight is equal to mg, isn't it? Mg. So m is what? Volume into rho. Okay, so volume again, area of tube into H into rho into g. So pi by 4 into d square into H into rho into g as equation 1. Then the vertical component of the surface tensile force is equal to sigma into circumference into cos theta. Okay, so sigma into pi d into cos theta given as equation number 2. So from like for equilibrium condition means the weight of the liquid of H is balanced by the surface tension at the surface of liquid. So this is the equilibrium condition. So from 1 and 2, that means we are going to equate 1 and 2 at equilibrium condition. So it becomes H is equal to 4 sigma cos theta by rho gt. Okay, this say, and it can be rearranged again into H is equal to 4 sigma by rho gt, because generally we have theta is equal to 0 for clean water and glass tube. Okay, see, this is the your expression for capillary rise. The expression of capillary depression will be same. Okay, it's same, but we will have a negative value here. Okay, a negative value means it is denoting the depression of the liquid level. Okay, so for theta is equal to 0 for clean water and glass tube, and theta is equal to 128 degree for mercury and glass tube. So these two values you can remember for your numerical point of view. Okay, then your capillary rise and capillary fall will depend on what conditions. Okay, so from the equation only you can easily find out that it depends on the diameter of the tube. See here, capillary rise or fall will depend on the diameter of the tube, d. So in this, it is inversely related to H. Then surface tension of the liquid, obviously it is depending on surface tension of liquid. And last but not least, specific weight of liquid, or you can say rho g. Okay, combined. So capillary rise or fall depends upon the diameter of the tube, surface tension of liquid, and surface weight of the and specific weight of the liquid. Sorry. Okay, this is all about the today's lecture. Thank you for watching.